Okay, so this is basically a demonstration part of how I decided my uh, analytical logic of this state transition circuit. So my mission is basically circulating this of my student number, which is 400176387. So based on this, I can see I have two duplicate number of 0 and 7. So I basically just use one counter, which is 0 and 1 is enough. And then first thing I do is to make a state transition table. I label everything on the left and decide what's the next state. So it's basically like shift one unit downwards. And yeah, and then the first thing I just make it more. One of the simplification I did is to make C1, decide C1 specifically instead of use X. So I put most of 0 and 1 consecutive. So in this way, when I go to the JK determination, I can have most of the 0 and the 0 or X or whatever connect to each other. This will help me when I was doing the K map because like I need to basically square everything is X or in the same number. If they are connected to each other, I can like make this square as large as possible. Yeah, and then so when I firstly make the state transition table as this one. So I have most my 0 and 1 be connected, kind of consecutive, and then I just copy paste each single bits to determine J and K based on another rearranged JK flop based on the which is based on the state transition. Yeah, so I have all this table here. The next thing to do, I just copy it back to the state transition table, put them together, and then I just use the trick taught on the lecture, which is color code every row and use that color to quickly decide where is the series in the K map. Yeah, so in this way I can make the K map make totally I think 9 K map very quickly because one other thing I need to mention is 0. So for not K, I can simply see it's consist of only X and 0. That means I can simply put it like not K to the not is grounded, then it's fair enough. I don't need to do the K map for that one. So then I just do the K map, use SOP and POS, try back and forth to decide which one is optimized. What I mean optimized is basically have the largest this kind of square. Yeah, yeah. So this is actually the final version of my determine of my implementation. So I also have alternative design. So it is basically for some of the K map, for example, J2, J3, and J5, they have both like SOP and POS pretty much in the same level of complexity. But I eventually decided to use J2 and J3 as POS. This is because it's mostly because here they have a shared OR gate, which is Q1 or Q4. That means I can actually save an OR gate when I doing them in POS way. So as you can see also here, so I can basically save one OR gate compared to the others, and this give me the minimum number of gate I need to use. This is just kind of simplification of my design. Okay, so this is a part of Simulink demonstration of my design project. So my project is basically circulating my student number, which is 400176387. Yeah. So yeah, so I basically have just one counter to make duplicate 0 and 7. So let's start. So now I'm just force my interest as 4 counter 1, and let's see what happened. 4 0 0 1 7 6 3 8 7. So this is correct. Let's also see what's another words. So it's recording everything. So it's 4 0 0. Counter is 0, counter is 1. 7. No, sorry. This should be 7. And then 6, 3, 8, 7 contests 1 and recycle back to 4 and yeah, goes on. So this means it basically works.
Okay, so this is the design project. My project is basically circulating my student number, which is 400176387. So I have to duplicate 0 and 2 duplicate 7. So I basically just use one counter. So in this way, I'm just making a 4-bit binary digit to represent it. So this is my circulation. Start at 4 counter as 1, and then go to 0 counter as 1. 0 counter as 0, and 1 as 0, 7 as 0, 6 as 0, 3 as 0, 8 as 0, and then the second 7 as counter as 1, and circulating back. Yeah, so this is basically the logic, and the detail of K-map and the design is showing the writing part, but basically I have this kind of logic here. So in this week, I will not just use some kind of diagram because that's still very complicated, but I just demonstrate my logic here. So this is the assembled circuit. So I can basically quickly go review every module. So I have my power supply, and I have 3 JK flock chips. And here is maybe merged by the wire, but it's basically three over there. So which they're from the left to the right, they're basically Q1, Q2, Q3, and on the top right is basically Q4, and the top middle is C1. So basically, it's going to this way. And I have my AND and OR gate. So this one is the OR gate, and this one is the AND gate. Yeah, and then I have my decoder as here, which is 5511 dB or whatever. But basically, it's for cancel, and you can see it works for a 7-digit display. And I also have a LED indicator labeled at here. So from the left to the right, they're representing Q1, Q2, Q3, Q4, and another LED as C1. Yeah, and I also have my range-lizer here. So basically, I have put everything I need to set and preset together here, and with another plug to the positive. So in this way, if I just plug off, it can immediately range-lize to my initial state of 4 counter as 1. Yeah. So okay. So this is basically how it works. So let's first test whether this is functional. So I started as 4 counter as 1, which is here. So I start. Okay. So this is circulating 4, 0, 0, 1, 7, 6, 3, 8, 7, which is basically correct with all the counters correct. Yeah. So what I also want to test is to see whether it's robust enough. So I will try another different state of 4 counter 1, or instead of counter as high, I use the counter as low in this case. So let's start. 4, 1, 7. So like it skips to 0, but like it's eventually just get back to its mean of the circulation. So that means like in this design, this circuit is also very robust. Okay, let's go to the final part of this project. So firstly, I list every result get together in this final analytical step. So what I find is they're basically the same and very consistent. Every method excellently do its job. The only thing I want to point out is that physical measurement maybe have some issues. This happened while I was doing the troubleshooting. Before I was doing this, I found my decoder not working. I do several debug and I figured out that the issue comes from like the somehow the input from the resistor is not high enough. Like it doesn't have high enough voltage to activate the decoder. Then instead, I just disconnect that and reconnect the decoder directly to the JK flip flop, and then my like flip flop works. Yeah, so I think the reason this happened is basically the protection resistor for LEDs or whatever. They also have the resistance, and it will share some voltage. If my input output voltage is not high enough, even though it's still like rated as high, it will like just make a force low when like the voltage is not high in real circuits. In Multizen and the analytic solution doesn't have such an issue because they are solve this question logically. It like this is basically just a quantitative error, and if I do this in quantitative way, it won't affect. But like for like the real circuit, it will be affected by this quantitative error. But anyway, it still did work, so I still call it excellence. So for the reflection in this project, what I learned is basically a step further of homework 7. Homework 7 is basically what I learned is about what the concept of sequential logic circuit or a finite state machine. So in that case, I can only understand, okay, it can circulate for some numbers, but I have no control about what is circulating in this circuit. But now after this design project, I find like how can I like make full use of the state transition table to break down every JK flip-flop behavior, and then use the K-map method to determine like what the specific logic to do the specific things. And in this case, I have the control of the sequential of the finite state machine. So in this way, all the applications such as this one, I can use it to express or like save my student number as some kind of information in the electronics. This indicates how the upper level machines such as the computer and the computer works. when they are calculating and memorizing things. Like this, my student number. This is just a very little information, but for computers who is basically like memorizing all this kind of writing I made, this is a lot of information. But it still depends on the same kind of strategy and logics. So I can see this is very interesting, especially for me who is not in the in the electronic stream at all. Yeah, it's very fascinating. I haven't sort of see this kind of stuff before. So in summary, I specifically also learned like two kinds of points. So firstly, I first know how K-map is working and how it can be used to determine and implement some specific logic. And one specific things I realized from this project is that when I have massive K-map and sometimes optimization is rarely necessary. In this case, I alternatively use SOP and POS method and do a table to see how many chips or the logic gates I need to use eventually. This will like help me make an optimization to decide what's the simplest logic to like implement some information I want. And the second thing I learned a lot about is the state transition table. So I realized that state transition table is a very helpful tool to organize information and indicate what's the next step. Like if I don't know this, instead of like using the K-map, I need to spend a lot of time just thinking of this massive 5 JK flip-flop circuits. This will be very hard to think of if I consider it as an integrity. But state transition table provide me a way to break it down to like 4 independent JK flip-flop, and then by applying the K-mapping, I can like decide a specific logic for each one. Yeah, so another trick actually I learned specifically in this project is the color coding. So like I realized that this is super helpful when I do like massive K-mapping things, when I have like 10 to 9 and 10 K-map to determine. The color really help is really super helpful when I like want to locate specifically one series in the K-map. If I don't have it, it will be it really takes a lot of time, which is just to locate the position. The other application of color coding is in multi-dynamic physical build-up. When I like color code the wire I used for each specific logic gate, it will be super helpful when I debug it. Like before, when I do multi, I use the same kind of a color, and when it goes wrong, I have no idea like what's going on. Like everything looks the same. But when I have the color coding, I can like do the troubleshooting very easily because I can like identify each logic just by color instead of all kinds of numbers and alphabets. Yeah, and this is also helpful when doing the physical build-up, which is the same way working as a multi. Yeah, so that's it. This is mostly what I learned about the design project or like the digital circuit course part.